In this lecture module, we shift our gaze to what eventually became known as reaction times. We'll see how this categorization, which wasn't a native categorization, but instead a synthesized categorization to understand and unify a particular set of phenomenon, develops, how it becomes operationalized, and how it eventually makes its way into mental chronometry and the study of the temporal development and sequence of development in mental operations. We'll begin our discussion of this topic by looking at astronomy, and specifically a controversy regarding the observation of transit times in astronomy at the beginning of the 18th century. We'll see how the work of Bessel helped to conceptualize these differences as what eventually became known in astronomy as the personal equation, in order to identify and minimize error introduced into the observations of astronomers. Astronomers develop instrumentation to accurately measure these discrepancies, both within an individual observer and across observers, as well as statistical techniques for analyzing those discrepancies in order to minimize their impact on astronomical observations. These tools then migrate into the work of physiologists who themselves are many of them accomplished physicists, and we'll see how they adopt and adapt these tools and this conception in order to, for instance, measure the speed of neuronal transmission. The successes of Mueller, Helmholtz, and Du Bois inspire, for instance, Fechner to adapt and expand these techniques into the Nessian field of psychophysics. The 17th century marks a relatively dramatic increase in the amount and the quality of observational astronomy. This increase in the quantity and the quality of observational astronomy is driven in part by an interest in astronomy, but it's also driven strongly by the need for accurate star charts for the purposes of commercial navigation. In order to navigate a ship in open water, one needs to be able to determine its position by reference to the stars, and this requires that you have charts that depict the stars' position at particular times with great accuracy. As a result, astronomers are working very hard to create more and more accurate star charts, and this requires greater and greater precision in their observations. One of the most important observations in doing this is the observation of transit time. This movie that's looping on this slide is illustrative of transit times. This is the moon's transit time across the sun. Astronomers of the time were using transit times of stars as they passed over the meridian of the observatory, that's directly atop the observatory, by accurately recording the time where the star passed over that observatory and comparing it to accurate observations of that star passing over the meridian of other observatories and other positions on the Earth's surface. The astronomers could more and more accurately triangulate the position of the star at any given point in time. This required ever increasingly precise observations of transit times. And as astronomers began to make more and more precise observations of transit times, discrepancies between astronomers started to emerge. A famous discrepancy that emerged occurred at the Greenwich Observatory. Neville Mescaline, the head astronomer, started to see discrepancies between his recordings of transit times and the recordings of transit times for his assistant, David Kennebrook. He assumed it was Kennebrook's fault and fired him, but different discrepancies with other astronomers began to emerge, and this prompted Frederick William Bessel, the gentleman pictured at the bottom left of this slide, to investigate this. And so he started to get astronomers using the same equipment to make observations of transit times, and he would compare their observations that they made, and what he discovered was what he called an involuntary constant. That is a slight difference between these astronomers, and as you explore more, you realize that even within an astronomer, there can be variations in the accuracy of their observations, and of course, across astronomers, even more likely to have variations across their observations. This eventually becomes named the personal equation by David Pond. Astronomers need to compensate for this source of error. One of the mechanisms through which they help to develop more accurate means of controlling for this error is the development of the chronoscope. This is Matthias Hupp. He was a Swiss clockmaker who creates a very accurate chronoscope. The chronoscopes allowed astronomers to make more and more accurate measurements of transit times, and this allows them to make more and more accurate comparisons between transit time measurements. And then Gauss introduces the notion of a statistical analysis of the mean error of these differences, and that allows them to account for a great deal of the error that's introduced through individual differences in observation. So we have the appearance of a phenomenon, a source of error, that gets categorized under the notion of a personal equation. The development and refinement of instrumentation and measurement of that error together with statistical analysis results in its minimization in empirical research.